Great. So, right. Well, like I said, thank you for coming. So we'll jump straight in. So, for those of you who haven't been to any of this series before, or for those of you who have never been to a Dublin Data Science workshop, this is a bit more interactive and kind of hands-on than a talk. So basically, it's me presenting work I've done via a workbook. But at the same time, I'm more than happy to have interactions and chats and whatever. If you have any questions, rather than just go through the messiness of muting and unmuting, maybe we can do that at the end. But if you do have any questions or anything, please just pop them into the chat. And I'll get to them as quickly as I can. I kind of have two screens here. So I have the worksheet that you could probably see on the screen is to my right. And then, I'm keeping an eye on the chat and the participants list and all that. And yeah, if you have any questions or, anything that I'm not really discussing very well, please just either unmute and interrupt me, or probably easier is to just put something into the chat. But I'm more than happy to have this be a little bit led by you. I don't have a particular, I have a rough idea where I think I'm going to get to, but it's more about, everyone understanding, or at least having some sense of where I'm coming from, rather than me getting through the material. So basically, what we're doing today is we're working on building customer lifetime value models, but we're doing it through Stan. And the main aim of all of this is for people to learn. I'm kind of trying to teach Bayesian techniques and the Bayesian approach. And the way I've kind of discovered this, one of the problems, I've been using Bayesian techniques for about 10 years now, maybe a bit, yeah, about 10 years. And one of the problems that I've always found with them is that when you're taught them, you're given very kind of toy examples, and suddenly it's a bit like the teacher going through, the simple equation and then giving out normal equations for homework. Because what I found with a lot of people is when they try to use it in practice, they kind of get stuck almost immediately, because the basic concept of being taught in a very, with a very kind of simplistic approach, which is very, very defensible, because some of these, there can be quite a lot going on in these. So sometimes you don't want to spend too much time discussing, the problem itself, because then you get this conflation between complexity and, complexity of the solution and complexity of the problem. But I kind of realized that I wanted a good real world problem to try and discuss and get into the nitty gritty of it, and also do it over the series of, a sequence of workshops, so that we can kind of get into some of those issues. So last year we gave, in 2021, we gave a series on data science soup to nuts, which is all available on YouTube. And one of the original plans was to learn customer lifetime value models. But it proved to be too complicated and just beyond the scope of what I was trying to achieve with that series. So I realized actually I was going to do customer lifetime value models, and also I kind of realized there was kind of a few attempts to do these with a Bayesian approach, and I found a few things that were decent, but there's been no really particularly good coverage of it. So I thought, okay, this is great. I can kind of learn this myself, and this will help me with this technique, and also kind of show to you these are the kinds of things you have, because these models haven't worked for me straight out of the box, and that's something we might get to today. But most models don't, unless you've got a very, very simple one. So this is kind of a good place to kind of show you, so that people don't just give up immediately or go, oh, throw my hands up, this doesn't work, and talk about different things. So so actually, let me just show you one quick thing. I will go quickly to the retail data. Excuse me, because I have this here. So we have a data set that we got online that we used for the workshop last year. And we had, why did that happen? I'm gonna have to check that. Okay, that shouldn't kick in, but excuse me. So we have a data set of transactions from an online data set. We talked about all this before. If any, it's on the UCI machine learning repository. It's a set of data from some kind of craft type store. The transactions go from late 2009 to late 2011. So it covers about 2 years of data. It comes in an Excel sheet that you download. I think it was part of some machine learning competition or whatever. And it's literally just, it's a single table with, and this is pretty much what it looks like here. You can see there's an invoice ID, a stock code, which is all the different items, a description, which is a free text field, the quantity of items sold, and what the date of the invoice was, what the price was, and what the customer ID and the country of the customer. So it's a very, from a complexity point of view, there's not that much going on there. There's only 8 or 9 fields. And obviously, you know, all the transactions within a particular invoice all have the same invoice ID. All the customers have the same customer ID, you know, and I've done some work on that before. You can look in the other series. But basically what we want to do is to take that data and to build what are called customer lifetime value models from that. So a customer lifetime value is exactly what it says. What you're trying to do is, what you're trying to kind of guess when you see transactions with a customer is you're trying to sense which are my valuable customers, and like, how do I measure that, and what are the various ways in which I can, you know, essentially quantify the value of a customer to me. And there's a whole bunch of different ways of doing that. And the one we're kind of focusing on is what are called buy till you die models. So the underlying principle there is that when a customer is first transacts with you, and most of these are done in a retail setting, like, so it's customers buying, although the and I'm sure if those of you who have been here before are sick of hearing this. I think the original work on this was done by an investment bank trying to get an assessment of their customers, and their customers were like calling up to make trades that they would then earn a commission on. And that was what they were trying to get a sense of, like, who are my valuable customers and how many customers do I even have, that kind of thing, trying to get a sense of all that sort of stuff. So that was kind of the basis of these models. So we have all this data, and, you know, we can do a whole load of things on them. This is all on the YouTube, on previous YouTube videos in previous workshops, and all the code, by the way, is on GitHub. So all this code here you can see is available. I'm pretty sure most of you have the GitHub repo. If you don't, let me know, I'll give it to you during the break. But yeah, so from that, then what we try to do or build, like I said, buy till you die models. So the idea is that a customer is born on the system, transacts throughout time at a regular, you know, transacts, and then stops purchasing, at which point the customer dies. And the way these buy till you die models work is typically they will break it down into what are known as Rfm models. So there's a recency, a frequency, and a monetary. So the idea is, what you're trying to do is you're trying to get, well, it's not quite an RFM, sorry, that's bad. You've got a frequency model, which is how often does a customer transact. You have a lifetime model, which is how long will the customer stay a customer, and at which point will the customer drop off or churn, as the you know, customer churn. And then other models as well will also add in the monetary element. So given that a customer has transacted, how much money does that customer tend to spend? And that allows you to kind of discriminate between customers who, you know, like, for example, transact very, very frequently, but relatively small amounts, versus those customers that transact very infrequently, but tend to spend a lot of money when they do. Because, you know, from a point of view of an organization, both of those are probably quite valuable customers, but they might need to be dealt with in different ways, and being able to figure out which is which can be very, you know, is often quite important. So basically, like I said, there's a whole bunch of models out there that work for this kind of stuff. And, you know, I tried to fit a few of them as part of the workshop last year, and realized these things were kind of complicated, a lot more complicated than I actually kind of originally expected. So what I'm trying to do is look at, in particular, we're looking at a version of those buy till you die models, initially called the PNBD model, or the Pareto negative binomial distribution. So by that, what I mean is that essentially most of them ignore the monetary, and we're going to ignore the monetary part for now. We will hopefully have time for it at the end. But in the monetary, in this PNBD model, we essentially break down our model into two parts: a frequency part and a lifetime part. And in the frequency part, we essentially model every customer as transacting at a fixed Poisson rate, right? So by that, what I mean is that a customer is essentially assigned a Poisson rate that it will transact at throughout that customer's lifetime. So it doesn't change. It's not time sensitive, or there's no memory or any of that kind of stuff. So is everyone familiar with the Poisson distribution and like measuring count data? If anyone isn't, let me know and I can quickly discuss it. But that's basically the idea. Now, again, of course, this is from a model point of view. This isn't necessarily reality. And we know that probably giving a customer a single Poisson rate for the entire lifetime of the customer is probably somewhat unrealistic, and also it doesn't account for things like seasonality, for example, or at least doesn't properly account for it. But that's, you start with a relatively simple model and see how far you get on. So that's kind of the first thing you do. So on the frequency side, what happens is every customer gets their own Poisson rate. And what they've done is they've basically said, but how do we assign that frequency rate for the Poisson distribution? Because that's just a continuous number from 0 to infinity, right? And then, well, what we do is we say, okay, each of these Poisson rates are drawn from a gamma distribution. So it's kind of like a hierarchical model. So at the top, we have a gamma distribution. So if you can think of it in terms of the data generating process, when a customer appears on the system, we draw from a gamma distribution, and that gives us a number from 0 to infinity. That number then becomes the Poisson rate that we then draw a number of transactions from. Or we'd look at it the other way, and instead of think of it in terms of a count, we can think of it in terms of a time between transactions, which is the exponential distribution, because essentially the exponential and the Poisson distribution are kind of like the inverses of one another. So we have a gamma distribution feeding into a Poisson, and when you look at the maths of that, that's a negative binomial distribution, which is where the NBD of PNBD comes from. And then secondly, we also have a lifetime model. So in the same way that a customer is assigned a transaction rate, the customer is also assigned essentially a lifetime, an average lifetime. And that lifetime is dictated by an exponential distribution, which also has a kind of a transaction rate. And that will tell us how long the customer is going to last. And that is also coming from a gamma. And a gamma that feeds into an exponential is a Pareto distribution. It's a Pareto of the second kind, I think. And there's a few different types. So essentially, it's got a very long tail. And what happens there is, because the gamma has a longer tail, and the exponential kind of has this long decay, what happens is you get an outsized number of customers with very, very long lifetimes, which represents the Pareto tail on that. So we have these kind of two components. We have this frequency model. And just so we're clear, and I appreciate I might be repeating myself, when a customer is given the Poisson model, it transacts until the customer lifetime is reached, at which point the customer dies. Okay, and what we're trying to do is, from using the various transaction data, we're trying to get a sense of those values, and that's what our model is trying to fit. We're trying to fit basically all these parameters so that ultimately at the end of this model, every customer will have like some kind of inference on the customer frequency and some kind of inference on the customer lifetime as well. And that, we kind of play off the two of them. So that's basically where we're starting. And if you go back through our previous workshops, we started with the frequency model. So we looked at basically some modeling Poissons using like hierarchical, using prior distributions and all that kind of stuff, and use of conjugate priors and all that kind of stuff. I don't really have time to go into it again, but go back and look on the YouTube videos if you need it in a bit more detail. But essentially what we have is we have like a gamma prior feeding into a Poisson, and what we're trying to use is essentially model the frequencies based on that. So we have a lifetime for a customer, which I will get to a little bit later, but we then have a count of transactions that occurred within that period of time. And then we kind of use the time that we observed the customer and the number of transactions that were observed, and that gives us an inference. We can then use these to perform inference on our frequency model. And that's kind of where we got to. And we had a very flat frequency model. So, what we would do from we would take the lifetime of the customer. Now, okay, I realize I'm talking very quickly and I've probably prompted a bunch of questions. Does anyone have any questions about what I've said so far before I move on? There's a chance there. Just pop something into the chat if you need me to explain anything. So that was kind of where we got to. Now, the other thing we did was we didn't use, I realized very quickly that actually using real world data for this stuff actually confused a lot of the issues. And I was trying to understand some of the basics. So, and also trying to separate out frequency from lifetime is kind of problematic. And that's something we'll talk about a little bit later. So rather than use the real data set initially, what I did was I went off and generated synthetic data sets. So basically, my logic was that I used the model to generate a synthetic data set. And the idea is then I should be able to fit that model in Stan and recover the original parameters. Now, that kind of sounds like a stupid process because it sounds like a waste of time. It's kind of like saying, okay, well, if I take 2 and multiply it by 2 and then divide by 2, do I get 2, right? Well, that sounds really stupid because we naturally think these processes are invertible. It's not necessarily the case. You can have models where you know that you lose so much information trying to fit your model that you're actually not able to recover the original parameters. And yes, Greg, I'm going to get to that. And actually, what has started to happen in Bayesian circles is they actually use that exact process. It's called simulation-based calibration. So what you do is, when you're trying to fit a model with your data as a way to validate, not necessarily just the model, but also to make sure you haven't like coded it badly or you haven't made mistakes in doing stuff. And that's often what they're trying to do. You basically use your model to generate a synthetic data set, fit the synthetic data set with your model, and then make sure that you can recover your parameters. And if you can do that, then it tells you that at least your model is internally consistent, right? Now, what we're actually about to discover, not so much on the frequency side, but very much so on the lifetime side, is that we're actually struggling with that because of the nature with which we're kind of observing our data and the way we're doing things. The recovery of those original parameters isn't as good as we would like it to be. And we will talk about that a little bit later. But anyway, so what we're doing is instead, for example, for our frequency model, we're basically assuming that every customer has the exact same lifetime. So we're kind of ignoring the fact that, you know, different customers will have different lifetimes and that can skew the frequency rate, right? So what we're going to do is we're just going to assume that every customer has the same lifetime and the same value, and also not necessarily that they start at the same point in time, and that we get a series of transactions and that we can observe the frequency rate within that. And that's basically what I did. There's a data set, there's a worksheet in here that will let us that lets us basically generate all this data. So we have let me just go up to the top. We kind of have our very simple data set. So you see, this is just a quick visualization of customer transaction times using our synthetic data set. And we see that, you know, I generated so that all customers were born on the same day and they all start transacting on the same date. And then you can see basically that, you know, there's random intervals between them based on the different Poisson rates that they have. And you can see, you know, it's not near, even though these have, you know, different Poisson rates, you can see they're not necessarily as regular as you would expect them to be. You know, but again, randomness is often very hard to detect with the naked eye. So these is all just Poisson realizations. Well, I should say exponential realizations for the time between. But all these counts would follow the appropriate Poisson distribution. And so, you know, so we can see all these. And what we're trying to do is use these observations to get a sense of the frequency rate. So how do we do that? So, well, basically what we do is we always ignore the first transaction because that's the first time that the customer's transacted. So from the point of view of the Poisson rate, it's the starting point, right? And then what we do is we just observe how many transactions we saw over the period of time. And that essentially becomes our count observation that we can then fit into a Poisson model. So just to show you that, and I'll show you a quick Stan model here. So let me just zoom that in, probably make it a bit larger. Yeah, so you can see here, this is kind of our Stan model. So this is our data. So our data is basically the number of data points that we have. How many customers did we observe? we have the by till you die count, which is the observed number of transactions, which is basically n-1, where n is the total number of transactions, because if you remember, we ignore the very first one. And then transaction weeks is the observed time period. And one of the things we discussed was, in one case, we knew that the lifetime was 1, but in practical terms, in real world, we don't actually know that. So the only way we can estimate a lifetime is basically from the starting point to the last observation. And that's kind of an estimate of the last time. Now, that's going to bias our estimates up if we do that, because what we're not allowing for the fact is that there may just have been no transactions between the last one and the customer ending. So we can see that because we know that all the transactions went up to the 20th of January, we can see that there's all this period of time that isn't going into the denominator for the allowable time. So essentially what happens is when we use that method, we have a tendency to bias our estimates up a bit, because we're essentially taking the same count, but we're reducing the denominator, the observation period. So that, like that, and that's something we definitely observed, and we talked about that more in previous ones. So yeah, so that's kind of, you know, and we can see here we have that. So the parameters in the model, we have a lambda for every customer, and then our observation, which is just our model, is that the Poisson log probability mass function is just the number of observations over the amount of time to observe, which is just the frequency rate, which is just lambda times the period of time, because lambda is a rate, and the unit of time we're using for all of this is weeks. We could use months, we could use years. For this period of time, because it was a shop, weeks just seemed like the better metric, but maybe months might make sense too. And it doesn't really change. It doesn't have, at least conceptually, it doesn't change things. It can change things from a numerical computation point of view, but we can get into that later. And certainly between weeks and months doesn't make that much of a difference. For that, I just kind of went with weeks. And then generated quantities, and then we're just, you know, generating a log likelihood value from that. We're just getting it straight out, because sometimes there's various validation things we can do if we have the log likelihood. So the value at the end of all this, you know, we do our sampling. At the end of all of this, we end up with a posterior sample for every lambda, for every customer in the data set. And while we have a lot of generated data, you know, we did a couple of checks on this. We did a bunch of different things. You know, we kind of looked at interval coverage. We looked at uniform prior and gamma priors. You know, we compared some stuff. I'm doing a very quick thing on this. So basically what we're doing here, and this is like a Q value distribution. So what we have is we have how many, I'm trying to think how many variables within this. Is there 2,000? That doesn't seem right. But anyway, for every customer, we end up with a posterior distribution for the lambda value. But because this is like a simulation thing where we actually know the true answer, what we're going to do is we take, for every customer, we take the distribution of the posterior distribution for that customer's frequency. And we know what the true value was that we used to generate the data, because this is a synthetic data set. So what we do is we create like an empirical CDF of the lambda frequencies. And then we see, well, what was the observed value? And that we can basically get the CDF value. So it's a number between 0 and 1. And where does it land? Where does the real value lie on that empirical distribution? And what should happen is, if you have a relatively well calibrated output, you should recover a uniform distribution, because some values will just be very, very high and the posterior won't discover it, or the noise itself was quite low. So you could have someone, for example, who, you know, over the 52 weeks had a transaction rate of once a week, but only happened to transact 3 times in the year, just due to random chance. And the bigger the data set is, the more likely those extreme values are to occur. So what should happen when you kind of do this Q distribution on each individual customer for your posterior, so every posterior, so let's say the posterior sample size had 2,000 iterations in it. Well, that gives you a CDF of 2,000 data points. With the real value, you pop it in, and you can use ECDF to do this, and that's what I did. And that gives me now a distribution of Q values, and that Q value distribution should be roughly uniform. And we can see we have it here. But what's happening is the low values are being biased up as opposed to the high ones. And that what's happening there is, so basically what's happening is if you can think of the probability distribution as being like my hand, and then, you know, on the y-axis, and we have the real point here, what's happening is the posterior distribution for lambda is skewed upwards, but that kind of ties in what we said, because the denominator was biased lower than it actually should have been, because all we could really work off was the period of time that the customer has observed, right? And that would be better if we had a true value of the lifetime. So, you know, we have that there, and then we've comparison plots, and you can see, you know, we did all of this before. Okay, so that's a very quick whistle stop tour of kind of where we got to in the previous few weeks. It only took me half an hour. But I wanted to go through it in, you know, a bit of depth, because there's quite a bit going on. Okay, so we have kind of that, but like I said before, we kind of have we've introduced an implicit bias into our model knowingly. And the reason why we're knowingly doing it is because in the real world, when we're working with real data, we don't have this nice window where we know the customers were born on this time and they stopped transacting at this time. In reality, the real world is messier, and customers are leaving and joining, and the whole thing is, you know, gets much messier. So over a period of time, you know, things get weirder, and it's harder to assess how long the customer is around. And in those models, we don't have the benefit of saying start and stop. So we kind of have to use the start time and the stop time, and kind of accept that there's a bias in there, unless we model the lifetime as well. But we've kind of very explicitly not modeled the lifetime for this part of it. We're literally just trying to get a handle on the frequency rate. Okay, so we've kind of willingly accepted kind of a less ideal model for this particular part of the process. So that's fine. So now what we would like to do is, but the way we've built all these models, if we look in here, let me just bring up some code here. When we're fitting the model, we've actually kind of hard coded in this prior. So if like I said, when we're looking at the Stan model, where is it? Should have you know what? Let me just show. I'll just bring it up here. It'll be easier. Let me bring it up again. So we have the Stan code here, and it is freak model prior, right? So we have this, so you can see here the B2B, and then we're basically saying that lambda is now drawn from a gamma distribution. But again, we have the Poisson observation there. But we see that every lambda is tied into this gamma distribution that's parameterized by R and alpha. And what we've had to do up to this point is kind of tell the model what that prior value is. What are the parameters of that prior distribution? But in reality, it would be better if we didn't do that, and we instead, you know, the Bayesian way to do this is we don't necessarily know what these parameters are. So therefore we'll put another prior distribution around them. And this is when you get into like what's called a hierarchical model. So rather than worrying about you kind of have it like this, right? So you have a lambda is coming from R and alpha, and then R and alpha are coming from these higher distribution values. So we kind of have a two-step process, which is a hierarchical model. So we've got all these values down here for the customers, and they're all the transaction rates. They're all coming from a gamma distribution, but we don't really know what the parameters of that gamma distribution is. We want the model to fit those for us if possible, right? And then, because that also tells us some valuable stuff about our population as a whole. And, you know, depending on the data, and if the data permits it, then you can actually go hog wild on that stuff, because you can start cohorting your customers based on what they're buying or what they're not buying, or when they joined the company, or when, you know, when they started transacting, or if they bought certain types of items, or if they purchased things during a certain time of the year. There's all sorts of these other things you can do. And you can let the model essentially tell you these kinds of things, right? But, you know, the problem with this is sometimes this doesn't work, right? And so this is why we're kind of trying these things out. So the other problem we have is that when we try to do inference on a gamma distribution, is that quite often there's problems with that. And gamma distributions can be difficult to fit. And this was kind of something I discovered firsthand when I first started working on these models. And the problem is that, like, so if we think about, say, a normal distribution, right? A normal distribution is parameterized naturally by its mean and its variance, right? So there's the mean, which is this measure of location, and then there's the variance, which is the measure of dispersion, right? But the natural parameterization for the gamma doesn't have that. It's got these two shape parameters. There isn't, one of the natural parameters is not a measure of its location. So instead, what we were going to do is, rather than parameterize it by its shape and its rate, right? We're instead going to try and use a location parameter mu and the coefficient of variation CV, which is just the standard deviation divided by the mean. And the reason why we do that is this seems a bit weird, but essentially, rather than trying to fit the two parameters directly, because that introduces a correlation between the two. So these two kind of become non-independent to one another, right? Whereas we can reason much more naturally about the measure of location and how dispersed this value is, right? So that if we can kind of put parameters on those two values, well, then we can just use the algebra to recover the shape and the rate, which is the R and the alpha. So in this case, basically for the gamma distribution, we can fit a location parameter mu and the coefficient of variation, which is CV. And then we convert them to the rate and the shape. So just the R parameter is just 1 over the coefficient of variation squared, and alpha is just 1 over mu times the coefficient of variation squared. So I know that looks a bit weird, but then basically there's a thing that allows you to do that because the transform parameters. So we kind of get this automatically. So what we're saying is that we're basically saying that rather than modeling, so we've got lambdas, then we've got this gamma distribution, which has an R and an alpha. But we're not necessarily saying that we know what the values in R and alpha before, like we were in our earlier models. We're now saying that there's a distribution for R and a distribution for alpha, and they're determined by this coordinate transform into mu and CV, and we're putting distributions on those values. Because then we can start to think, well, I don't really know what what's the average rate of the customer. Well, I can kind of put some distributions around that, but then I have to kind of do some mental gymnastics to convert that into a rate and a shape. It makes much more a shape and a rate. It makes much more sense to actually put distributions around the quantities that we kind of understand, and then just use the transform block to make sure we don't mess up the maths, right? And that's kind of how that allows us to start doing some quite interesting things. Now, coordinate transforms are not always straightforward. So you do get these things like Jacobians, and it's not a complete gimme to do this kind of stuff. And sometimes you have to think about, if you're transforming from one coordinate set to another, you also have to call what's called a Jacobian, which is this matrix for the transformation, and you've got to get the determinant, the Jacobian, and include that as an adjustment into the model. Luckily, we're not doing any of that stuff here because these things are all much simpler, but sometimes you do have to do that. But usually, as long as you kind of code it in with data parameters and transform parameters, kind of Stan takes care of all that for you. It just kind of falls out in how it works on the background. So basically, like I said, we've got this R is 1 over coefficient of variation. So instead of having parameters of R and alpha, we now have these parameters, the hierarchical mean and the hierarchical coefficient of variation, right? So these becomes our parameters, plus we have 1 for each of the lambdas in here. So each of our customers gets their own lambda, but then they also kind of feed in to this hierarchical distribution, or the hyperparameters that feed into it. And then we can put some distributions around then. And then, like I said, we now have R is just 1 over the coefficient of variation squared, and then alpha is just 1 over the coefficient of variation squared times the mu. And then we can put a gamma distribution hierarchy on the mean and the coefficient of variation. And those we can kind of reason about. We pass those in as parameters instead. So we're still passing in values for our distributions, for our, at some point, basically you have to just put hard numbers on things. But now we've kind of moved everything up a single level so that we can we're now kind of talking about the parameters of the hierarchical distribution rather than the parameters of the individual customers themselves. And that gives us a good bit more power. And it also means we can actually then, like I said, start telling us the customers, how do I phrase it? The posterior distribution will start telling us what the mean of the customer frequency is and what the coefficient of variation is. Okay. And we just kind of, I don't want to say it just happens, because clearly Stan is a bit more complicated than that, but that's basically what we're trying to do. We're trying to squeeze as much data out of this as we possibly can. So we let's have a quick look. I think I showed the code here. Yeah, like where is it? Sorry. Yeah. So we have, and it's not much more complicated. We just have a bit more data going in. We have parameter 1 and parameter 2 for the distribution of the mean, and parameter 1 and parameter 2 for the distribution of the coefficient of variation. And they're just shape and rate again. And then we have these parameters. We have a transform parameters here, which are going to handle the R and the alpha for us. And then the hierarchical mean, the hierarchical coefficient of variation, we plug them into the lambda. So we've just added a couple of extra lines to account for those things. Everything else pretty much stays the same. Okay, and then we can fit our model, and we run our model, and we get all these samples, and then it pulls out, and we can see now that we now have, these are 2 parameters that we can actually, start to perform statistical inference on. So we check the various HMC diagnostics, no divergent transitions, tree depth is satisfactory, everything looks okay. So, I mean, we don't know for certain, but we've got a distribution of the hierarchical posteriors. So you can see and again, we get both the sample values and the transform parameters. So we have R and alpha as well as the mean and the coefficient of variation. So what we see here is that the mean of this distribution is about 0.29, let's say, maybe a bit kind of hard to say because it's a little bit skewed. Say 0.28, 0.29. So that's the average customer transaction rate, and the coefficient of variation is just under 1, right? And that's kind of what the data is telling us. And that's we can go back and compare that to the real values that we use to generate the data on, to see how, and we can see the alpha value, which is just under, it's about 4 and a bit, and the R is just greater than 1. So it's basically an R of about 1.1, 1.2, and an alpha of about 4. So, we're an overall rate of about 0.3. And then, we can compare that to what our data was and see. So let's quickly do that. So we, and I didn't talk about this yet, but we have this generate transaction data sets that we used for the data. And I think we used 1 and 5. Let me just check. I should have had this prepared in advance, but I didn't. Where is it? Yeah, 1 and 4. So it should be about, so it's slightly higher. We're estimating a higher frequency than the data suggested, but we kind of know that because, as we said, we have biased our estimates up by the fact that we're using just the observed lifetime of the customer. But we kind of know that's wrong because we know a customer doesn't necessarily stop transacting as soon as the last transaction was made. Based on how our model works, we have a separate value, which is a lifetime value. So if the customer happens to, transact a good period of time before the lifetime hits, we're just going to have we're going to upwardly bias our transaction rate. So that's not too bad. I mean, it's not perfect. It's not perfect at recovering, but at least we're kind of in the ballpark, allowing for the fact that, we would expect these issues to kind of manifest in this kind of way. So, so that's actually quite good. Now, but again, we want to do our posterior distribution. So again, we can see this should be a uniform distribution of the Q values. So once again, every customer gets their own distribution of lambda values. We know what the true value for that customer was. We get the Q value from the ECDF, and we get a Q value realization. It's a number between 0 and 1, and that should be roughly uniform from 0 to 1. So this is kind of what the, given the bars, we have 50 bins in this histogram. So this is kind of what it would be, just a uniform distribution if it was perfect. But again, you can see we've still got this slight upward bias represented by the fact that we're overrepresented on the lower Q values, because what's happening there is if the true value is here, our posterior distribution is biased upwards because of what we introduced in terms of how we were calculating the lifetime of the customer. So that's, that's not too bad. And again, like I said, this isn't our final model, because A, we're working on a synthetic data set, and B, we're not really properly accounting for the lifetime of the customer yet. And that's something we're going to kind of work on next. So, so there we go through that. And then, we validate our models. We're kind of doing all these kind of things, doing these Q values. We get some, sometimes, and then the other thing we can also do is transaction counts. So rather than just compare the lambda values, another way of doing it, because again, we're trying to build for the real world where we don't know the true value of the lambda. That's what we're trying to find out. We can only work with what we have actually observed. The other thing we've done now is, in the period of time that we used our different lambda values to sample from the Poisson distributions, and then just compare the observations and what do they look like. So we have the observed number of transactions from each customer, and then each of those 2000 lambda values, we do a draw from a Poisson. We now get a distribution, like some kind of a bell curve of counts of transactions. So if we do an empirical CDF of that, where does our count fall in, and what does that look like? And we can see, we're getting a slightly different quantiles, but that kind of makes sense because you're dealing with discrete ECDFs there. So you're not, it's going to be very much kind of rough step functions. So it's not really surprising that the uniform distribution there is much clumpier, because if you look at an ECDF, because it's only a fixed number of counts and it's relatively small count data, you might have a distribution of counts for a year going from, 5 up to 15. And you'll have a certain number at 5 and a certain at 6, a certain at 7. And so therefore you get this kind of step function in your ECDF. It doesn't really look like a nice smooth curve. So it kind of makes sense, again, that we would see a less pleasant, I don't want to say more unpleasant, but a clumpier distribution of count Q values. And that Q value trick, by the way, is very, very useful for validating models. It's very useful to do, like it's kind of the equivalent of what they call QQ plots for fitting parameters to see how well a probability distribution fit matches the data. But yeah, that whole Q value approach and using it for like simulation-based calibration can be very, very useful. So yeah, and then we're going to do the same thing. We're going to use our validate our frequency model to construct the data and allow us to compare multiple models at once. So we're now going to kind of use out of sample data. So all of this stuff was in sample. So we were essentially reoccurring the data. Now what we're going to do is we're going to try and basically check how well do we do if we move out of data. So let's say in terms of thinking it conceptually, if we think of, we fit the data for this period of time and we get, a reasonably happy model fit, but in reality, we then test it on a piece of data later in time. So kind of like test, train, validation. And how does that work? And, as you might expect, that doesn't work quite as well. But, it's not too bad. We're putting in some hierarchical parameters, model comparison plots, and where are they? Yeah, so we can see we've got a bunch of different values. We're basically combining all the different models that we built. So we've got a flat prior where we don't have a gamma prior at all. We just say it's a uniform distribution. And then we have a gamma, which is a kind of wider gamma, the 0.25 to 1. We have a tighter gamma, which is 1 and 4. So the same mean, but a lower coefficient of variation. And then the hierarchical. And you see, when you do these QQ plots, suddenly you actually start to get pretty decent, much better results when you go tighter, because basically what's happening here is we're kind of closer to the true values that we actually used to generate the data. But we can also see here that with the hierarchical model, Actually, that kind of is similar to the gamma. So what's happening here with the hierarchical model is, as long as we're kind of in the ballpark with our parameters, the model itself kind of allows, it's called partial pooling. So it's kind of like the thing that regularization does in machine learning. What happens is that when you allow the data to kind of learn from all the other data points by putting them as part of one single distribution, it kind of forces the more extreme values to get shrank. It's called shrinkage. The estimates become less extreme. So if you have this like crazy value for lambda, like crazy high value for lambda, because you end up with a, in the real world, let's say, for example, you just have a customer who transacts very frequently for a short period of time and then stops. That will manifest itself as a very, very high estimate for lambda. But in reality, what's happened is it's just a freak of random sampling. And in reality, we really want kind of the fact that we know that it's very unusual to have a customer like this. It's more likely that this is just random chance. What happens is learning from all these other customers to tell us that allows us to move this estimate in closer to the body of the rest of the data. And that's kind of that's the power of hierarchical modeling. It tends to give us these better calibrated fits for the data because it's called partial pooling. So basically in those areas, those subsets of the data where we don't have a lot of data. So for example, it's a very low frequency model, or it's a very, so you just don't have very many count observations. Or areas like if you're cohorting your data and you just don't have very many samples in that cohort. The fact that you can actually learn from the other areas of the data, it just improves your estimates of those low data set ones. And you can kind of, what it allows you to do essentially is if you have lots of data in a particular cohort, then the data estimates kind of dominate. But in those areas where you don't have a lot of data, you're kind of smoothing out these extreme values by your knowledge of the other cohorts. And that's kind of the power of doing this in the first place and why we would kind of want to do it. But, getting there takes a little bit of getting used to. So I've just noticed the time. So it's about 10 to 8. Like I said, I normally take a break for about 10 minutes in here to let people go to the bathroom or grab a cup of tea, or more importantly, if they have any questions, pop them in the chat. But I'm going to leave it there for about 5 or 10 minutes. And yeah, and when we come back, we're going to, I'm kind of finished on this, but if anyone has any questions, because I'm very conscious, I'm coming into this cold because, we missed last month. If anyone has any questions about the frequency model, I'm more than happy to go back and cover that stuff again. Just, spend 10 minutes at the start, or if we have a gap in the break. But failing that, yeah, what I'm going to do now is it's about it's almost 5 to 8. What I'll do is we'll come back at 8:05. And yeah, and if anyone has any questions, please just pop them in the chat. I'm going to turn off the video for a couple of minutes, but I'll keep an eye on the chat and put myself on mute. And when I come back, I'll be back in 2 or 3 minutes. I will get onto that. Great question, Greg. Give me about 2 or 3 minutes and I'll address that when I come back. But yes, if anyone else has any questions, please pop them in the chat in the next minute or two. Okay, I'm back. Greg, are you there? You just ping in the chat if you are. Okay, sorry. So your question is, the diminishing returns on increasing hierarchy? If so, is that experience? I presume you mean in terms of like, oh, well, I don't know what the prior hyperparameter value should be, so therefore I'm going to add another one and keep going up. So the short answer to that is yes. In practice, no. Sorry, in theory, no, but in practice, yes. In theory, you could do that, although all you're really doing at that point, unless you have like different ways of distinguishing those hierarchies. So let's say, for example, you have different cohorts of customers, and you're giving a different prior distribution to each of those cohorts, and then those values are going up a level. So if you don't do that, if you're just saying, okay, I don't know what this value is, so I'm going to add like a third level, then all you're really doing is coming up with a much more complicated prior. And the danger with that is that sometimes you end up with too many degrees of freedom in your model, and the data can't actually properly, you create what's called identifiability issues. So essentially, if you have too much freedom in your model just ends up not being able to distinguish between, you know, this combination of parameters over here and this set of parameters over here. And you end up with like what's, you know, a multimodal distribution, which is pretty bad. So in practice, and also the other downside, so that's one downside with going with too many hierarchies. The other practical problem with it is that from a numerical point of view, when you're dealing with finite, if you're dealing with infinite sample sizes, that would be perfectly fine. But one of the issues you have with dealing with finite samples is that you can end up with essentially what are called funnels and various ways in which the model can't properly resolve, not from an identifiability point of view, but you essentially have to reparameterize your model, because you end up with this kind of very pathological behavior because of that combination of the probability model you've built and the data you're trying to combine. Because like a fit is never just one or the other, it's always a combination of the both. So you can't say that this is the right model independent of the data, because you can have and this is from using Bayesian statistics in practice in a lot of areas, primarily in insurance. What you can often find is that you will fit the model on a subset of your data and it works perfectly fine. And then you'll add one or two extra bits of data, like a new category or something, and the whole thing will explode, because the model that you've built to fit your data works fine on a subset of it, but as soon as you start adding in this extra data where it doesn't really work, the whole thing kind of blows up. So a lot of this is kind of practice. Hierarchical models are very, very powerful, and you can have multiple levels of hierarchy, and that does happen, but you generally need a combination of a good reason to include all those multiple levels, a way to combine them, and sometimes it requires a certain amount of finesse, let's say, to actually get the bloody fit thing to fit properly. And what happens is, and this was I talked about this in some of the earlier workshops, what often happens with Bayesian samplers is that because they're not just trying to create an optimum value, it's not an optimization process where you're just trying to find a set of values for the parameters of the model. What you're actually trying to do is create a joint distribution for all the parameters on the model conditioned on the data. What will often happen is that you will find problems with the model itself that manifests itself when you try to fit a stand model that don't manifest themselves when you use techniques like MLE and stuff like that. Because it's a much more complicated process conceptually. You're trying to map out an entire, you know, topological landscape, whereas all you're trying to do is climb to the top of a hill with an optimization process. It's also why it absolutely is a power tool, yeah. So what typically will happen is you will have people who, using more traditional tools, the tools work fine, because what happens is the fact that you're only trying to do an optimization kind of hides these issues with the model. Now, that's both good and bad. It's great because you get an answer. it's bad because the answer could be wrong and you don't know why. And it's why typically when one of the first things people learn when they start working with Bayesian statistics is to adopt a zero tolerance attitude to divergent transitions, because what that is telling you is that the answers that Stan is giving you are wrong, like they are biased answers, in the sense that the posterior distribution you are sampling from is not the posterior distribution you're trying to create, and those problems are manifesting themselves as numerical issues, and that's why it reports. That's why Stan always gets this grief for not working. So what actually got me onto this originally was when I tried to fit a bunch of these models on the data set from the UCI data set for last year. I actually had a lot of problems with fitting them, and I realized that, oh, wait, there's actually issues with these models, and this is something I've actually found. When you try to start introducing hierarchies, if you don't introduce hierarchies and you don't build a hierarchical model and you just kind of set parameters, things seem to work fine. But the real use of these is to start building in a couple of hierarchies and getting inference at the cohort level. And I have found issues with this. Now, again, it's like, I can't say the model is wrong because that's clearly not true, but there can be issues where your particular data set is difficult to fit with your Stan model. And one of the reasons why I still think Stan is really good is it actually tells me that, and it informs me very loudly and very annoyingly in a way that then provides me an opportunity to try and remedy those issues. I appreciate that was a very, very long answer to your question. Okay, please keep the questions coming. Does anyone else have any questions? I'll give people about another minute. I said it's about 3 minutes past. So I'm aiming, I'll go on. We're going to talk about lifetime models in a sec. For those of you who haven't been here before, I generally go on until I won't go till the full 9 o'clock. I'll generally try and wrap up around 20 to 8:45 and let people head off. But then if people have questions where they want to hang around later and, ask me to go over some of the topics or whatever, I'm always more than happy to do that as well. But yeah, while we've got another minute or two, does anyone have any other questions about what I've been talking about? And I should probably reiterate, I appreciate I've gone through the I can indeed. I appreciate I've kind of done a very quick whistle stop tour of the frequency model here, but the reason I did that was because I kind of covered them a lot more in workshops 2 and 3. So, and this is the 4th one, and I don't want to keep kind of repeating old ground. So I talk about them a lot more in the previous ones. If any of you have any questions or anything, I can indeed, Greg. Let me just scroll back up. So like I said, we're trying to fit, let me hold on 1 sec. It probably makes more sense. Yeah, if you look at it. Yeah. So we have a lambda, right? And we have this gamma, which is an R and alpha. Okay. But what we're trying to do here is we don't necessarily want, we've got a hierarchical distribution on these parameters. So rather than fix R as a number and fix alpha as a number, what we instead want to do is put distributions around those two values and then make inferences on those two parameters and allow the data to give us a posterior distribution in R and in alpha. Okay. However, from a sampling point of view, R and alpha are correlated with one another. And this is apparently, I didn't know any of this. I've known about the gamma distribution for a while, but I realized kind of as a result of this about last year, and I started looking into it. And apparently it can be a known issue in some data sets that the gamma distribution can sometimes be quite tricky distribution to fit because of this correlation in the two parameters, because neither of them are a measure of location or a measure of dispersion. So in particular, what we do is we're instead saying that we're going to split R and alpha into two other parameters, which is the mean and the coefficient of variation. Okay? Does that make sense? Okay, right. Now, so we now have a mean value and we have a coefficient of variation. But these are two values we're going to infer. So we're putting a gamma distribution on those values. And the gamma distribution needs two parameters. So we need two parameters for the measure of uncertainty around the mean, and two parameters for the measure of uncertainty in the coefficient of variation. And let me just show that. So basically, when we've put in the data here, I can actually show you with the code. Well, is that right? So instead, so this is kind of what I'm talking about here. We don't necessarily know what the mean is, but we know it's going to be somewhere from, 0 to 1, 1.5, right? We don't necessarily know. We kind of have a sense that, let's say, the average customer, the distribution of values for the average customer is going to go somewhere from, say, 0.5 to 1.5, or from 0.2 to 1.2 for the mean of the overall distribution now, not for any individual customer, for the overall distribution. Now, to be honest, we could probably go with a tighter one because it's the overall average customer. We probably actually have a sense that it's somewhere from 0.2 to 0.5. So we could probably bring that in if we had to, because it's the overall distribution average. Right? And I know this gets a bit weird trying to think about, it's the mean of the whole distribution, which is a narrower, the average of the average, right? So what typically happens there is when you're talking about averages of larger distributions, the region of uncertainty is typically narrower than it is for individual customers. So any individual customer will have a much wider spread of values than the overall average of the distribution. So we've you can see this is the prior distribution for mu here. So it's going from somewhere from, say, 0.01 or something like that all the way up to 1.5. That's probably too wide. But let's include it anyway. If the data tells us otherwise, it'll bring it right in. Okay. Now, we don't want crazy values either, but at least, there's nothing too ridiculous there, like 10 or 15 or 20, which we know is a preposterous number for the average. But it can cause problems. So if we do end up with too wide, this is why you have problems with like uniform distributions and stuff. If you end up coming with totally ridiculous values for a model, then the prior ends up putting too much probability mass out there, and it causes the model to have fitting issues. So if we had problems with this, we could very easily narrow it. Okay, and similar for the coefficient of variation, we don't really know where that is, but we know, again, it's the standard deviation divided by the mean, right? So that was one I kind of couldn't value, but I figured just looking at values, if it's 1, it's not too bad. If it's a bit lower than, say, 0.5 or anywhere, and you can see I've put a much wider prior on that. It goes anywhere from, slightly above 0 to 3, because again, I don't have a better sense for that, and that's okay. I mean, as an initial guess, if you're more uncertain, you make your prior distribution wider. So I kind of fit those two values in, and those are the values that I'm putting in there. So if you look here, this is a shape of 2 and a rate of 2, which is the two parameters for the prior distribution on the coefficient of variation. Okay. Does all that make sense? Yeah. The one thing I will say about this is, because as I'm saying this, and I'm a bit rusty myself because it's been a month or two, the way to learn this is to actually take my code, download it, and run it and play around with it. It took me a while to kind of grok some of this stuff, and you only kind of learn it by kind of doing with it and playing around and kind of getting a sense of it yourself. This isn't really stuff you can kind of learn academically. You don't really grok this kind of stuff until you play with it. Okay. All right. But you saw there, even though we had those relatively wide priors, once we kind of narrow it down, we see that the mean is much tighter. It's somewhere from, it's saying that the distribution of the the average mean is somewhere from 0.26 to 0.32, let's say. And the coefficient of variation is somewhere from 0.85 to 1. So the actual data has massively reduced. The prior to the posterior the data has had a big influence on narrowing that right down. So if we really wanted to, or we wanted better fits or whatever, we could probably reduce those priors. It wouldn't really affect our probably as much, but it might speed up things. Sometimes getting priors right can really speed up the fit times and things like that. There are, it can affect performance. So it's not just a question of always doing this kind of thing. So sometimes that's a good test as well. Whereas you throw all your data in, but instead of running it for like 2,000 samples or 3,000 samples, you run it for like 100 or 200 and just play around and check the speeds. And what you sometimes will find is if your priors are tighter or not tight enough, you will notice a big difference when you start changing the priors, even though the underlying inferences aren't changing very much. In some cases, the sampler will just sample much quicker because it has to do less work because the prior isn't putting it into areas that the data doesn't support. And that will happen too. Okay. All right, so we've kind of done with frequency model, right? We've gone through all that. Like I said, so now we kind of but like I said, we have this problem where we've biased our data because we've kind of ignored the lifetime model, right? And while in theory from this data, we know that the lifetime of each customer was a year, in practice, we didn't have that observation. So we kind of were reducing it down to the last known transaction time. So we kind of need to do something similar, and we need to perform an analogous thing to get a sense of the lifetime model, right? So now we're going to look at lifetime models and how do they work. So again, there's no point in using this data. Instead, what we're going to do is we're going to flip this around. So rather than have a synthetic data set with a fixed lifetime for each customer, we're now going to have customers with a fixed transaction rate, and now we're going to sample their lifetime model, okay? And then we're then going to use that to try and make inferences on the lifetime of the customer, okay? So how's that going to work? Now, automatically, we're going to encounter a couple of problems. And the problem there is that we don't necessarily know how long, we don't have good observations of the customer lifetime. So, here's some data that we've got. These are customers we've sampled, and this is from the real data, I think. Is it? Yeah, this is the real data set that we were looking at that I said we're using synthetic. So you can see here, we don't necessarily have a good feel for the customer lifetime because we know that, we have a kind of a sample for the rate. We can kind of see when the customer was born. It's when the first dot is, right? But we don't necessarily know when the customer died, right? Now, we know all those customers have probably churned at this point, right? Because, by the time we were observing 2020, right, we don't necessarily, we can kind of see most of these customers based on the transaction rates we saw before. They're likely to have churned at this point. But the point we're making is that we don't have an observed point of time for when the customer has churned, right? So our lifetime models are going to be more problematic because essentially we have censored observations of the lifetime. So we know that the customer was still alive the last time the customer made a purchase. So we know that in these final rightmost dots here, the customer was still alive. So we know that the lifetime was at least that length. But what we don't know is we don't have a good measure of after that. So essentially, we've just got censored values. And so this is kind of going into the realm of like survival analysis and things like that, where we're dealing with censored observations. However, this is actually worse than that because in most survival models, you have a mixture of observations where you have a fully observed observation of the lifetime, i.e. because the event happened within the period of study or whatever. But in this case, we never have a proper observation of the lifetime, because we know we don't actually, like, the customer never actually tells us when they churn, right? They just stop transacting. And the point is that they may have, the way the model is built, there's a lifetime value, and then customer, like, as in how long does the customer last for in terms of time, and the transactions happen within that window. And at some point, the transactions are going to stop. And that point in time of transaction stopping doesn't necessarily coincide with the time of churn. In fact, almost always it doesn't coincide. It will just happen to be, and we've got that period of time. So we can only really work with the censored observations that we've got. Now, we can deal with that in Stan, and we can actually model that. However, what happens is that we get a lot of problems in observing this. Okay. But the other thing we want to do is we also want to get a sense of, well, okay, so given that we have a customer transacting, over a period of time, well, like, let's look at it here. We can say, okay, well, we're seeing a transaction here, and typically the way it works is we're combining the two, like I said, and this is something we won't talk about in this workshop, but probably in the next one, I'll start introducing combining both lifetime and frequency together, because both can inform one another. But what we'd like to do here is just to get a sense of transaction times. What I'd like to do is to get a sense of the time between successive transactions, because what we could do then is we could at least say then, okay, well, I don't necessarily know if the customer has transacted, but if the amount of time from that we last observed a transaction from the customer is more than the most we've observed from any customer, well, then the customer has probably churned. So we can kind of put a minimum value on the lifetime and a maximum value on the lifetime. And if that's not too bad, then we can start to, essentially at least top and tail our observation. And maybe that'll be enough to at least give us some kind of sense of the lifetime inferences that gives us something we can work off. Okay, so what I'm doing here is just to have a look at the time differences, and we can see here that almost all time differences are less than 75 weeks, but the vast majority of times between, and this is just modeling the times between the transactions, in most cases it's less than 25 weeks. Okay, so what we're going to do here is, so we do the exact same thing that we did before. We're going to take a transaction of a customer, right? We're going to draw from a gamma distribution to give us a rate parameter, but rather than feed that into like a Poisson for a count variable, we're instead feeding that into the exponential distribution, and then we're drawing from the exponential to give us an observed lifetime for the customer. Okay, so let's say, for example, and the average of that is, it basically is similar to the Poisson. So the exponential parameter is the rate, and it's the inverse of the rate is the average lifetime. So if we, let's say we have, and you can kind of think of it as a drop off. So if we think of it in terms of, like, let's say it's weeks and the exponential distribution is in weeks and it's 0.1. What that means is you can kind of think of it as we're checking every week. There's a 10% chance the customer will churn or die or whatever, and then stop. And then if it doesn't, okay, it's now 2 weeks and we check for 10% chance again. 3 weeks, check. And eventually at some point, the check will fail. And that's our observation of the exponential distribution. Now, I'm making it very, very simple there, but that's roughly a way to kind of think about how the exponential distribution works. And so you can see how it's kind of the inverse of the Poisson distribution that way. Okay, so whereas, because in reality, of course, we're not dealing with a unit of time, it's instantaneous, like differential increments in terms of, and then you take the limit as as it gets smaller and smaller and smaller, and that realization then gives us our exponential distribution. But you can kind of think of it as the same way as like the drop-off rate. So in the same way that we had an average customer rate of transactions, you can kind of think of the rate of the lifetime as roughly what the overall churn rate of customers are, right? And that's kind of a similar way to kind of think about, or just think about it in terms of the average lifetime of the customer, and work it that way. So the first transaction is considered the birth of the customer, and then the second is so we've kind of generated synthetic data here, and we're going to fit some flat models to get the lifetime. So we're trying to fit observe customer lifetimes, and we've got some stand models in here. So I've got, again, I have some training stats. So I have a data set here where we have a bunch of customers. Instead of having a fixed lifetime, they now have a variable lifetime, but they have a fixed transaction rate. So we can observe a fixed count of transactions occurring. We don't particularly care about that point because we don't really care how many transactions they take. All we really care about is that they make transactions at a fixed rate until they die. And at some point, they will have made a final transaction, right? And that kind of gives us the lower bound on the lifetime of the customer. And we do that for every single customer. And then we fit that into a model, okay? So, you know, again, we fit this out. We can use our stand model. Where is it? Here it is here. So we have a similar idea. We have a minimum lifetime and a maximum lifetime. So like I said, the minimum lifetime is the time between the customer starting on the system and the final transaction timestamp. So the timestamp of the final transaction that the customer made, that gives us our minimum lifetime of the customer. And that's a right-censored observation. We know it's at least that value, right? And then we also have the maximum lifetime because, like I said, if the customer lifetime is larger than a period of time that we say, if a customer hasn't transacted for, say, 50 weeks, we just say the customer is churned, right? And we can, you know, that's another way of doing it. That will give us a high-end value. And then maybe that will give us a bit more resolution. Now, in practice, what happens is, because there's so much variation in the customer, generally that value doesn't really add much. Basically, it's the same for everyone, and it's basically right out at the tail of the lifetime observation. So in my experience, the maximum model, using maximum and minimum and just using the minimum value, you don't actually get much difference between them. I was kind of hoping that we would get more between them. So yeah, so we sit now. The question there is, well, if we don't actually have an observation, an actual observation, how do we fit the exponential distribution with it? Well, we can use these very interesting LCCDFs. So ignore this thing for now. We have the log CDF. So basically what we're doing is, and this is kind of how survival models work in Stan. Again, we have this kind of curved distribution of the values, right? I'm assuming everyone is familiar with these. You know what? Let's use some graphs for this probably. So let's say, for example, we have let's go REXP. Let's fit 10,000 values with a rate of 0.1. So we have all these values, right? And then let's just put them into a exponential vals. ECDF, exponential vals. So that gives us a function. So now we can go from 0 to, say, 100. So sequence 0 to 100 by let's just do a ggplot of this. Should have prepared this earlier, but I didn't, so never mind. That's far too big. All right, so let's make that a bit smaller. Let us go to, say, 30 instead. Right, so I could probably go a bit higher. Let's go to 40 instead. Because it took me a while to get my head around this part, but this is a pretty cool aspect of Stan. And I think this is how some of the the various survival models work it as well. They do something similar to this. That should work. Why did that not work? It's there. There we go. All right, so this is the cumulative distribution function, right? So what this is telling you is that, you know, let's say if I move up here, right, and I draw up from the x-axis all the way up here and across, what it's telling me, let's say that's 0.65. What that is telling me is that 65% of the samples is less than 10, right? And that's why it's a monotonically increasing curve over time. Now, I'm conscious most of you probably understand cumulative density functions, but it's worth talking about, all right? So what we basically do is we don't have an actual observation for the lifetime. Like I said, we only have the minimum value. So instead, what we do is we say, okay, well, we know that the minimum value was 10. Oh, you still see the R. Oh, sorry. Hold on. Thank you. Let me just stop that share and share screen too. Sorry, thank you about that. Can you see it now? You see the curve? Yeah. Okay, so basically, if we go to 0.10, right, and draw a line up, we can see it's about what, 0.65, let's say, roughly speaking. Okay. So we know that when we have a left observed value, essentially what we're trying to do is what we would like to say is that the minimum value this is this value. And what does that tell us? And what's the cumulative density value? So rather than adding from the probability density function, we're adding from the cumulative density function, because that allows us to make inferences on minimum values and maximum values. Okay. And for a minimum value where it's right censored, we know that so let's say let's say a student was observed and a customer was observed, and it was 10 weeks after the last transaction occurred 10 weeks after the first customer's first transaction, sorry. Okay. Well, what that tells us is that essentially it's a minimum value. So we actually want the complementary density function, because we want the value to be the other way around. We want the curve to be the other way. So essentially, we will go 1 minus. So we get this kind of survival curve here. So we basically say that this value here, it's whatever this 0.35 or whatever 1 minus it is, right? And then because we know that whatever the parameters are, this is kind of what our cumulative probability mass is going to tell us, right? Well, okay. And then if it was a maximum value, it would be just the CDF, right? But we're working in log space, so that's why we have the log CDF and the log CCDF, right? So the minimum lifetime is the LCCDF, so it's the cumulative density function, but the C means complementary. We don't have to do the 1 minus, because basically all that is calculated for us, because trying to do it yourself creates a lot of rounding issues with numerical stuff. So by default, they kind of provide you both the CDF and the CCDF, so that when you get censored values, be they left censored or right censored, which in this case, the minimum value means it's right censored, as in that's the minimum value. We know it was beyond that. And when it's left censored, it basically means, well, we know it had definitely occurred at this point not at this point in time, but after this much time had passed, and it was somewhere before it. So we basically have these two values, and it's somewhere between the minimum and the maximum. And we can add that by just adding the LCCDF and the LCDF to it. Now, in survival analysis and things like that, we often have both censored and uncensored observations. So what we would do there is, and we don't have that here, but if we did, we would just literally do a switch. And if it's a censored value, we would do the LCCDF or the CCDF. And if it was an actual value, we would just use the PDF, the LPDF, like we did for the lambda function before. right? And that gives you a certain amount of, and usually what happens is that it means that you can use both fully observed and partially observed data to observe together. But in this case, we only have partially observed data because we only have effectively reliably minimum values, because even then the maximum values are probably just too big to really be of any value. They're all going to resolve in 100% probability, and it's not really going to give you any proper kind of posterior discrimination. Okay. So, okay, so and then we have some generated quantities that I'm not going to talk about. So that's basically what we do. We can just kind of plug those lifetime values in, fit our models, and see what we get. So we fit our models with the parallel chains. We check our fit diagnostics. So no divergent transitions. That's good. I was genuinely surprised by that when that occurred. No like EBFMI, everything seems to be mixed. Things aren't too bad. However, the problem is that in this model here that we were talking about, we did not put any prior values on the data. So what we're saying is that basically any value for the exponential rate from 0 to positive infinity is perfectly valid. And this is the downside that I mentioned to using. This is why I include it in here. The whole thing, oh, I was looking at the wrong thing. Yeah, when you get it, you just get a whole lot of divergent transitions. And the reason you get those divergent transitions is that yeah, hang on, why do we, sorry, I've confused myself here. That old fit, where did we get the, yeah, I got a load of errors in this. So the checking sampler, no divergent transitions count. Okay, that should, there's something weird going on there. I'm going to have to check that out. Basically, it doesn't work, because what happens is we've basically said any positive value for the exponential rate is valid from 0 to positive infinity. So basically anything at all is valid. So all those extreme values, if we give everyone a farcically long lifetime, right? Well, then those minimum values, of course, are perfectly valid. They're perfectly valid within, if we say that every customer is going to have a lifetime of like 10 million years, right? That is as equally valid because we've given it a uniform prior. So I need to check that out. There's something going wrong there. That was blowing up before. Instead, what we do, we kind of put a prior on it. So we have this gamma distribution on it here. We pass the gamma priors in, and then the model samples properly. Okay, yeah, and that should run. And now we can start doing our fits. That all executes fine and should give us, decent R hats. Maybe the R hats were wrong up there. No, they're all fine. Yeah, I'm not sure what happened there. I'll have to look that up because these were all blown up before with the flat model, and for some reason they seem to be working now when I reran everything recently. So yes, I may have put a bug in the code. That shouldn't be working. The R hats were like 5. It was crazy. And again, it's because our priors had said it's okay to have preposterously large values for the lambda rate, for the tau rate. And therefore, it just basically causes problems with the sampler and the whole thing blows up. Whereas here, because we have set our priors to say that we know the exponential rate, is say 0.1, or the average lifetime is 10 weeks, or the average lifetime is 5 weeks or 20 weeks, whatever it is, then suddenly we're getting resolution. The data is helping us resolve those values, because suddenly those minimum lifetimes are giving us information. Now, they're not giving us as much as if we had a full observation of the data, but they are giving us some of them. So, we're getting better values. But when we can check the Muse CC, hairy caterpillar, these are all our trace plots. And now we do our Q values and we see we have a problem, right? So we have the quantile value. This is exactly what we had before. We now have posterior inference on our mu based on our model, but we know what the true value was. And we're just getting typically our lifetime estimates are much lower. So we're getting the exact opposite here. All our lifetime estimates are up here, and our posterior distribution tends to be below it for the lifetime model. So if you think of it the other way around, it means we're estimating longer lifetimes, but the value is down here. And I think basically what's happened here is this is the problem that we have with this model, because, and this is an inherent problem that we're going to try and fix probably next time with slightly improved models and maybe tighter priors and stuff like that. But ultimately, because we don't have any like actual observations of the lifetime value of the lifetime estimate, all we have are censored observations. It basically means it's very, very difficult to properly recover the parameters with just looking at the lifetime model. Okay, but this is significant because it tells us that there are limits to the way in which we're doing our data, or essentially the way in which we can do our data. There are limits to how much the data can resolve in terms of the model we have constructed, and that will manifest itself a little bit later in the model too. And that's why I have been kind of broken all this stuff down and split into like a transaction frequency model and a transaction lifetime model. Because what I said, when I combine the two using stuff we'll talk about in the next workshop, I was getting these issues when we start trying to introduce hierarchies, and I couldn't really understand why. And building these kind of crappy synthetic models that I knew weren't really going to work and were going to throw us up issues, they provide us a lot of insight. And it also means basically at some point, the model just might not work properly. Like this might be a model, I don't think so, but at some point we might need to take a different approach. And there are alternatives in PA. We don't have to use PNVD. We can use the beta geometric negative binomial distribution, for example. And we will talk about that later on in the workshop, later on in this workshop series. And that uses a much simplistic model. But there may be cases where, even though we know that that model is flawed, at least we can get something useful out of it. Whereas, you know, slightly more sophisticated, more I don't want to say realistic, but more higher firepower models aren't going to work because of the combination of data that we've used. Now, I'm very conscious of the time, and I've been a bit, I don't understand what's going on there, and I want to look into that. So I think here is a good place to stop, at least in terms of new content. But basically, so let me kind of break it down again. So what we're doing here is, like I said, we're modeling the lifetime of the customer, and we're using an exponential distribution. So in the same way that we had for transactions, when a customer is born on the system, they essentially are going to get two values. They're going to get a Poisson rate and a lifetime rate. And those two values are going to feed into a Poisson distribution and an exponential distribution. The Poisson distribution will tell us how many times they transact, and the lifetime distribution will tell us how long they're going to be a customer for. Okay, and essentially those two are kind of related, right? Because the lifetime of the customer is going to tell us the window for which the transactions can occur. All right, so even though they're somewhat independent at the top, they become dependent on one another, conditional on the data. And that's something you'll often see, that, you know, conditional independence and conditional dependence. So what we're going to try and do, but to kind of get a sense of that, there was a lot going on in that model. And like I said, this was a much more sophisticated model than I initially gave it credit for, which is why I kind of decided it was out of scope for the workshop last year. So instead, what we're doing is we're taking the transaction model where we have a fixed lifetime so that we can just focus on the transaction part. And then in the next one, we're going to have a fixed transaction frequency so that we can just focus on the lifetime part. Right? The frequency model worked fine, but when we got to the lifetime model, we started to have problems because, as I said, we don't have an observation of lifetime. Our observations for the length of the lifetime of the customer is by definition censored, because we don't know when. We just know the minimum value that that lifetime could possibly be, because we know that this customer last transacted, say, you know, 50 weeks after the first transaction. And that's it. It's a very simple you know, it's a relatively simple concept. in that way. But kind of when they combine together, they become a bit more complicated, certainly for lifetime, because for the lifetime model, we can kind of tell, if we know that the customer is transacting on average once every 10 weeks, and the customer kind of goes 50 or 60 weeks without transacting, then we can start to say, oh yeah, we probably know the customer churned at this point, right? So at some point we can probably say there's a certain point in time that we can just call and say the customer has churned by this point. Although from a probabilistic point of view, that's not true. Sorry, I've gotten a question there. Thanks, mate. I'm not familiar, but is there a way to redefine so we can force at least? Yes, absolutely. Yeah, so that's a good point. With the limitations of the data that we currently have, there is no way to dictate when the customer churned. However, even in those models, the points that we're saying they're dying, all we're really doing at that point, if we say that, for example, that we try to take a payment off a customer and the payment gets refused, or the credit card expires and isn't renewed, we can then say that the customer definitely churned. Or we can say that we can pick a point in time at which, if the customer hasn't transacted for a certain period of time, we say that the customer is churned. But even then, we're not actually observing the point of churn. All we're really doing is setting the maximum value of the lifetime. So we kind of still fall into this problem of now you could fix it and just say, okay, we're going to make that a hard observation, or maybe there are certain applications where we can say that the customer definitely churned. For example, I think these models would actually work for claims development. So you could have, this is one of the kind of the theories I've had in my head, in that every claim is like a customer, and then we have basically the movements on the claim happen with a frequency model, and the times between them are dictated by that. And then at some point, the claim will close, and that would be a lifetime point. And then we would have an exact observation of the lifetime of the claim. So we would essentially have, every claim will have a certain lifetime, at which point the claim will close. But in the interim, we also have a transactional model that says the value will change, at these points in time. So it could be useful for that. That's what I was, and then you would have exact observations of the claim finishing, assuming, of course, the claim can't then get reopened, because that can sometimes happen too, and you might need to model for that as well. There are churn queues in call centers. I'm not sure what that means, Greg. Is that like customers who have churned who you plan to call back? I'm not sure how is that a hard observation though? How do you know that that is the exact point of time at which the customer left your system, if you know what I mean, and decided to no longer? Because usually you only can observe a customer lifetime at these very discrete points in time. You don't really know when the customer decided, I'm done with that, I don't really need it anymore. They just kind of stop transacting, right? And it's usually sometime after the last transaction. Now, there is a model called the BGNBD, the beta geometric negative binomial, which is a simpler model and is much simpler to fit. And they have a very different model for lifetime. What they basically say is that a customer, at every point of transaction, the customer has a probability of churning, and they churn at the point of transaction. So basically, every time the customer transacts, they're given a probability P of transacting. And then, at that point, you decide whether or not the customer is churned or not. And there's basically that, and that simplifies the mathematics a lot. However, the problem with that model is customers who transact more frequently have a tendency to be decided to be, because every transaction, the probability of them not churning is going down each time. So what tends to happen is they tend to underestimate the longevity of high frequency transacting customers, as opposed to low frequency transacting customers, simply because in any given period of time, higher frequency customers transact more often, so therefore get more opportunities to churn. But that is a way of dealing with that problem that you do. And then obviously you can get a lifetime from that based on the transaction model as well. But I'll talk about that, I think, a lot more. I think they're interesting models. I'm not sure. I know a couple of people who have used the BGNBD, and that was my first introduction to the topic because they had used BGNBD very, very successfully and were very happy with the models. I would definitely prefer to use the Pareto negative binomial if I could, because it makes more sense to me that, you know, the lifetime is somewhat independent of the transaction frequency, at least initially. Now, you might find that there are cohorts in that, but you know, that's something we can talk about. All right, so look, I'm going to wrap it there because I've kind of confused myself. I'm not going to lie. I need to look into this a bit more. I have found in general, however, and this is kind of the caution, and this is why I found these more sophisticated, getting my head around the lifetime model has been a lot more complex than getting my head around. I think because the observations are censored, and like the transaction model was just more intuitive for me. The lifetime model I found more complicated. And to be honest, from my, like this workshop, which is all available on GitHub, by the way, if you want to pull it all down and take a look at it and tell me if I've made any mistakes. Getting a handle on the lifetime side has been much more difficult. And generally, the model hasn't performed, like your posterior samples are just less powerful. Like the inference is a lot more woolly. I think it's just because you've got noisier observations and the whole thing is a bit kind of up in the air. So I think that at this point, I've kind of gone down as far as I'm willing to go on the individual models. I think at this point, we need to kind of combine the two together and try and get a sense of the combined model, which I will talk about more. I'll introduce the, I need to introduce kind of the combined model together, where you can kind of see both the frequency and the lifetime interact in a relatively, like it actually boils down to some relatively simple mathematics, actually, even though you end up with these kind of integrals in terms of calculating probabilities and stuff. Actually, the final, like the analytic answer for the likelihood model is actually relatively straightforward. It's not particularly complicated at all. It kind of boils down nicely, and yeah, once we introduce that, but this kind of woolly censored observations for lifetime, I think, can introduce problems from a practical point of view when you try to use these models in principle. But okay, I'm going to stop there. Thank you all very much for coming. Like I said, we have a talk in person for those of you who are in Dublin. I think it's the 30th of June. It's a Wednesday. I think we're going to have 2 speakers. There will be details on Meetup. But I will be back next month as well, probably the middle of July, and it won't be on a bank holiday, well, because there is no bank holidays in July, but it'll be on a Monday night, and hopefully I won't be in a position to confuse myself, because I'll have figured that out. There's something definitely wrong with that, and I need to fix that, and I only just noticed it there. But yeah, that's kind of where we're going to leave it. If anyone has any questions, now is probably the time to ask them. Yeah, and we're going to leave it there. Thank you for everyone who's came. Like I said, it's a complex model. It looks relatively straightforward. I think it's a lot more complicated than people give it credit for. And I'm a little bit concerned because I know some of these models have been implemented in an automated fashion in the various machine learning frameworks. Like I think Google automatically can take your transaction data and run these models. I'm not entirely happy, considering the problems that these models have found. I'm not sure I'd be happy to do this in an automated fashion, at least initially. I think I'd want to do, if I had a business based on this, I think I'd want to work with some of the transaction data first to learn the vagaries of this before I kind of productionized anything like that, because of these reasons. But anyway, yeah, I'm going to stop it there, and thank you all very much for coming and, you know, braving this very nice bank holiday Monday. And yeah, we will be back next month with the combined Pareto negative binomial model, and possibly talking about the beta geometric as well, depending on how we get on. But yeah, thank you very much, and I'll talk to you all next month. I'm going to hang on though, we've got about 10 minutes, so I'm going to hang on if anyone has any questions. But I think what I will do now is stop the recording, so that at least people can, just in case people don't want questions caught.